Well, good afternoon or good evening or good morning to everyone watching this video on Further Mechanics 1. We're in Chapter 5, we're in the last chapter that I'm going to record for this series on elastic collisions in 2 dimensions. Now, these are taken from Dr. Frost's Maths. The link is in the description if you want to get access to those. So we're going to start off in Chapter 5 by looking at an oblique impact with a fixed, smooth surface. So in this chapter, we're going to consider what happens when a sphere hits a wall at an angle other than 90 degrees, because 90 degrees is a bit straightforward. And we'll look at what happens when two spheres that are not travelling along the same straight line are going to end up colliding. Now, just a side note here, what this is talking about is this is where the wall is. Here we've got coming at a different angle, so if I show you on the pen here, we've got one angle coming in here and one coming out there, they're not on the same straight line. And the same idea here, where we've got things pointing in different directions, and they might be a pair of skew lines, potentially, and we know how to find the distance between skew lines using vectors if they were in a vectors question. It's a nice exam question to think of, that one. And they've not asked it yet. Maybe this year, 2024, they might ask it, I don't know. So, the key to all these collections in this chapter is that all the spheres and all the surfaces that we will look at will always be smooth. So you don't have to consider friction of the balls and things like that. At university level, you will start to consider what these things are when we're not talking about smooth surfaces. But for the moment, in Further Mechanics 1, we will only look at smooth. Anyway, so a smooth surface cannot apply a frictional force. It can only apply a normal force, that's important, and then the impulse is always normal to the surface, so momentum and velocity is only changed perpendicular to the surface. And the momentum and the velocity, technically, parallel to the surface will remain unchanged. So if we want to consider a diagram for this, we can look at a very similar diagram to what I just drew a minute ago, where we can have the wall down here, and we could have some particle. Let's draw a circle for the sake of it. Let's draw some force, for example, coming out there at parallel at 90 degrees. And we could have some speed u. That's our initial speed to the surface. And we could have that coming in at some angle, say angle alpha. And then using component parts, we could split this up into u times by the sine of alpha. And we could split that up that way into u times by the cosine of alpha. And of course, that will remain unchanged in the collision. So we'd have u cos alpha still continuing out the other side there. But what you would expect is that the speed on the rebound will be a smaller speed compared to u sine alpha. And the wall, of course, I think what I'm trying to get at here is that these will remain constant. I think that's what I'm trying to get at there. So, the two things that I would recommend that you learn for this particular chapter is that the component of the velocity parallel to the surfaces is unchanged, and perpendicular to the surface it will depend on what's known as the coefficient of restitution. Now, I could just give you a bunch of formulae, but that's not any use to you, so why not explain where this idea comes from in the next diagram. So, let's actually look at what this is going on about with the theory. So, theoretic-wise, we could split this up into its component parts. So let's do that. We have u times by the sine of alpha. Again, I'm assuming you know how to do this from normal mass mechanics. Times by u cosine of alpha there. And this speed, of course, continues on with v times by the cosine of beta. And then this up here will be v times by the sine of beta. Fairly straightforward. Now, if we were to resolve both of these speeds, we could have that u times by cosine of alpha is equal to v times by the cosine of beta. And this is because parallel to the surface, speeds are unchanged. Of course, I just mentioned that on the previous slide. Now, to get the next one, we need to remember Newton's law of restitution, the speed of separation divided by the speed of approach. But I don't like using it like that, so we're going to get v sine beta, but we're going to have some multiple of our u sine alpha, which is going to be this coefficient of restitution called E. EU sine alpha will be equal to V sine beta. Those are two very important equations that you need to learn off by heart. Now, this is Newton's law of restitution, perpendicular speeds to surface. Right, if we divide both of these now, so we could have the EU times by the sine of alpha there, we could divide it by the EU cosine alpha, because I know I can get tan alpha from there, pretty straightforward. And this will be V times by the sine beta divided by V times the cosine of beta, and you could probably tell me what that would be. But to write it out, you'd have E times by the tangent of the alpha is equal to just tan beta, because V's cancel. And again, you've done something similar when you were looking at in normal mathematics, where you were looking at the R cosine alpha formula and things like that. You were dividing to get the angles. It's fairly standard stuff, really. But all we're really doing here is resolving the speeds. A side note here, the angle of deflection is the total angle through which the path of the sphere will change, and that will be alpha plus beta. There's some nice questions coming up, but we might need that. So if we were looking here, let's say, we've got a vector 3 minus 3, so it will be going 3 down, and across to the right, we would have another 3. Just reading the vector off. And, well, E is a third, so this remains the same, because I've just told you it remains the same. But this, E is a third, so this will be 1/3 of this, which is 1. So your vector is 3, 1. It's that straightforward. Let's do this one over here, where we've got 1 down, 1 across. And E is 1. So the speed will be exactly the same. It's a perfectly elastic collision because E is equal to 1. So your speed will just be 1, 1. Straightforward enough. What about if E is a half? Well, if E is a half, it's the same idea. I'm going 6 down, and I'm going 7 across this time. Doesn't matter, if E is a half, then I'll just do a half of 6, don't I? This stays the same, I've just told you. So we'd have the E times 6, which would be 6 and a half, or 3. So we'd have the vector 7, 3. 7 in the y-axis, and then 3 up in the j. Straightforward enough. Finally, we've got, this is going minus 3, so it's going 3 down. That's where that's coming from, and it's going 5 across. And E is 0. So, actually, anything times 0 is 0. So this will end up being 0. So we'd have the vector 5, 0. That would be a perfectly inelastic collision, right? Again, we've talked about this before in chapter 4. Go back to that video for that. So then here's an example. We've got a smooth sphere S is moving on a smooth horizontal plane with speed u when it collides with a smooth fixed vertical wall. At the instant of the collision, the direction of motion of S makes an angle 60 degrees with the wall. The coefficient of restitution between S and the wall is a quarter. We want the speed of S immediately after the collision and the angle of deflection of S, which will not depend on the initial speed. And of course, we can look at this right now, shall we? So, this will be probably one of the few things we will do today, because I've just given you all the theory. So, we've got this wall going on, we've got this angle coming in. We're told it's at 60 with the wall, okay. And we will call that speed u for the sake of it. And then it will rebound with some speed v and at some angle alpha. We don't know what the angle alpha is. So, splitting it up into component parts, you'd have u sine 60, and you'd have u cosine 60, wouldn't you? And then, what else you'd have? V cosine alpha, split that up, you'd have v sine alpha, and what else we're total is a quarter. Let's write that down. Write down everything you know from the question, and then you go ahead and do your usual stuff. So, cosine of 60 is a half, so I can actually just jump straight away and write that as u over 2. And that is equal to v times cosine alpha. That's useful. And then sine of 60 is root 3 over 2. So we'd have u root 3 over 2 times by e, which is a quarter, is equal to v sine alpha. Now, I want to connect these somehow, and I've got an equation down here in the tip box which will allow me to do that, where I can just square them, because dividing them is not going to help too much. So let's square them all. Let's see what we get out here. V squared cos squared alpha plus v squared sine squared alpha, because I know a Pythagorean identity that connects those, is u squared over 4 plus 3u squared divided by 64. Well, that's going to be 1 in there, so I'm just going to get a v squared, combine them together. What's that going to be? 19 u squared on 64. So then I can just square root that, and I get what? Square root of 19 over 8 times by u. And v must be positive. That's important. Now, part B. The angle of deflection. Well, I didn't say dividing would help, but here you can divide, and it might help to get the angle out. So we'd have v sine alpha on v cosine alpha, and that's going to be equal to u root 3 on 8 from the second equation, divided by u over 2. Well, divided by a fraction the same as the fraction flipped, so the 8 and the 2 will cancel down to a 4, along with the u's cancelling. So this is just going to be root 3 over 4. And that's going to be tan alpha. So we can get alpha straight off by inversing tan on your calculator. And if you do that, fetch the old calculator there, the inverse tan of root 3 divided by 4 is 23.4 degrees. We'll give that 3 significant figures, because in mechanics we like giving things to 3 significant figures. And then we're asked for the angle of deflection. Well, I told you further up on the screen what the angle of deflection was. Let's see where I wrote it. I told you it here. It's alpha plus beta. It's the same diagram that we've got here. So all we need to do is do alpha plus beta, which is your 6 degrees, which is here, plus the thing we've just found, which is 23.4. So the angle will be 83.4 degrees. And that's how we do example 1 in the textbook. It looks a bit neater doing it like this, I think. I quite like these problems. And yeah, just a note over here, this one is quite useful if you're finding the speed, i.e. Pythagoras. This one's quite useful if you are looking for an angle, potentially. Okay? So, as we were saying, at this point in time, it might be good to have a go at questions 1 to 4 in exercise 5A, just to get you some practice with this sort of thing before we look at example 2, which is a bit more complicated because we've just got it on a slope. That's the only difference that we've got with this problem. And then we will leave you to it, and in the next video, we're going to stretch this idea a bit more. So, let's have a look at example 2. We've got some angle alpha, all well and useful. We've got some particle, which I'm going to draw. We've got a little bit of work to do here, don't we? So, it's falling vertically, okay. Bearing in mind, I've not done these questions before, so I'm just doing them as I read them. So, we've got some angle being dropped, haven't we? So, I'm thinking if I do it like this, then it might work. Something like this. Split it up into component parts. That's straightforward. And then it's bouncing off at some other angle, which I don't know. We'll call that beta, say. So here we have v cosine beta. This will be your v sine beta, won't it? What else do we know? That's going to be alpha anyway by basic trig. Because of your alternate angles, we can do that. I don't really need to explain that, do I? What else do we know? We know that tan alpha is a half, okay. Well, if tan alpha is a half, we know some things about trig, because if this is a half, I've got them the wrong way around, then this is just root 5 by Pythagoras, and this is our angle alpha. So we can get what sine and cos alpha are. Sine alpha is just 1 over root 5, the opposite. And if we're looking for the adjacent, for cosine, that's going to be 2 over root 5. That would take you a matter of seconds to do in an exam, but it's easy marks if you can write it down. Now, the coefficient of restitution is a half. We're looking for the speed of the ball immediately after the impact, aren't we? Now, I don't like dealing with things on slopes. I'm just going to make it flat again, but I've already resolved it, so this makes this a bit easier for us. We've got a speed of 5, we've got an angle coming down, we've got this speed across here, but we know some things, don't we? That's going to be what, 10 over root 5, isn't it? This is going to be 5 on root 5, just because we wrote it down there a minute ago. Make sure my angles are marked on. This was V cos beta, wasn't it? And this was V sine beta in that direction for an angle beta. Okay. We'll look for the speed of the ball. So if we're looking for speed, we can just square root them, can't we? Well, I say square root, we're just adding them together, aren't we, really, in effect? So, what do we want? We've got V times by the sine of beta to be equal to 5 sine alpha, which I've just told you is 5 over root 5, by what we wrote down there. But 5 on root 5 is just root 5, it's not very interesting, is it? V cos beta, however, I'll be slightly careful with that one. This is 10 on root 5, times that half from the coefficient of restitution. That's also root 5, coincidentally, there. So, add them, square root them. Just do the components of each squared. And if you do that, that will give you 10, won't it? Because square and square root cancels. So you'll just end up there with V is equal to the square root of 10. But the square root of 10 is approximately just bigger than 3, and so it's going to be what? 3.16. ms to the minus 1 to 3 significant figures. Most of the time, you'll be either squaring it with Pythagoras to get the speed, or dividing to get the angle. One or the other. So, at this point in time, questions 5 to 8 are good to have a practice of here. In the next video, we're just going to extend this idea a little bit more, because we're going to start to delve into what happens when we've got successive impacts, and essentially things will get a little bit trickier from here, but I'm going to do that in a separate video because it's a separate section, I think. So we'll look at that in the next video. Come back.